Hello, my name is Patrick Saenz from Southwest Research Institute, and I'm going to be talking about RISC-V processors for spaceflight embedded platforms. This presentation was prepared by myself, Patrick Saenz, Stephen Malone, Kirti Radhakrishnan, and Shahla Yousefi. Today, we'll be talking about the RISC-V architecture, soft-core processors. I'm going to introduce a research project with it, technical approach, the issues we encountered, the results from the research, the conclusion, reference, and then I will be ending with the questions. So what is RISC-V? RISC-V is an open source instruction set architecture based on reduced instruction set computer principles. RISC-V was designed to have a small fixed-based ISA along with modular fixed extensions that work well with most systems. Some of the benefits of RISC-V is the cost, no licensing fees. The RISC-V ISA is free and open source. Choices. There is many hardware ICs and soft cores that one can choose from. Modularity. There is a high degree of customization through disk extensions. Support. Software toolchain supports GCC and LLVM. Stable. Base and first standard extensions are already frozen. There is no need to worry about major updates. It is extensible. Functions and custom extensions can be later added into the core. So what is a soft-core processor? A soft-core processor is a hardware description language HDL model of a specific processor, CPU. Soft cores can be customized for a given application. This means that soft cores can be implemented in a wider range of devices, such as FPGAs. Some of the benefits is the cost. They are usually cheaper to buy a soft core rather than a radiation tolerant processor. There are many choices. So one can choose from a wide range of different architectures. They are very modular. There is a high degree of customization that one can do to the core. And in power, since there is many customizations, one can choose a low power processor or just use the extensions that would allow you to use less power. Some of the disadvantages are the speed. Soft cores are clocked at much lower speeds and utilization. There is a higher logic utilization, so less room for mission-specific logic. With all the advantages of RISC-V and soft cores, we wanted to determine the feasibility of using RISC-V as the next generation of processors for spaceflight embedded systems. The objective of this research project was to evaluate the performance of currently available soft-core processors implementing the RISC-V architecture on an FPGA and determine the feasibility of using these virtual processors in spaceflight applications as a replacement for current hardware microprocessors. The motivation for utilizing soft-core processors is to reduce the size, weight, power, and cost of hardware designs where an FPGA is already present and a standalone microprocessor might not be necessary. So with that, I'm going to turn over to my colleague, Shahla Yousefi.
Thank you, Patrick. Hello, everyone. My name is Shahla Yousefi. I am a research engineer at Southwest Research Institute. I will be presenting the rest of these slides. 2 development boards were needed to test the 2 main core architectures, as they are hardware specific. There are some notable trade-offs between the 2 development boards used. The Xilinx board had a larger FPGA with more logic elements, allowing for multi-core emulation, whereas the microsemi board has more onboard memory for running larger applications. Both boards were run externally with just a USB connection to the host PC, where the PCIe link was not utilized. These microsemi MI5 core configurations were tested on the PolarFire eval kit. The maximum frequencies were selected as the highest stable found by the rigorous timing constraint. The mid frequencies were approximately halfway between the maximum and 50 MHz, adjusted to have a favorable DDR3 clock ratio. At the time of testing, these 3 Copham-Gessler Null 5 cores were the only cores available for the Xilinx Kintex board. The compression extensions were not enabled yet. EX1 is a minimal single core. EX2 is a fully featured single core, and EX4 is a quad-core array of EX2 cores. They all have a fixed frequency of 100 MHz. 3 benchmark programs were selected to test various aspects of core performance. These are standard CPU performance benchmarks with widely available scores for many embedded processors. Whetstone was unable to be run on the microsemi MI5 cores or the minimal null 5 EX1 core due to lack of floating point instructions. The environments tested on each device reflect the most readily available software packages and compilers. The MI5 architecture also has an RTMS environment available, but after finding the bare metal performance to be subpar, further testing with additional operating system overhead seemed pointless. On the other hand, Cobham-Gessler provided RTMS and Linux operating system pre-built with the necessary benchmarks, and the performance with overhead was sufficiently dominant over the MI5 cores to remove the need for bare metal development. A suitable RTMS Whetstone port was not found for the null 5, but was able to be tested in Linux. The null 5 cores ran much faster and thus required larger benchmark iteration sizing to generate accurate benchmark scores. The team encountered several issues with the microsemi hardware and software. The planned MI5 core configurations, as listed here, were made legacy during the course of testing, and a migration guide detailed the switch to newer cores. These new cores will require a new development board, the Splash Kit, which was received defective twice with hardware problems. We should also mention that board replacements were delayed because of COVID-19 and IC manufacturing shortages. This is the first batch of MI5 benchmarks with the simpler and slower core configurations that utilize fabric multipliers. The smallest core without compression extension was unsurprisingly the slowest tested. Adding the compression extension alone granted a sizable performance bump with virtually no increase in device utilization or power consumption. Performance is scaled linearly with frequency, showing no memory bottleneck. There is adequate space on FPGA for multiple of these cores. For comparison, on bare metal, a Cobham-Gessler UT700 processor, currently in use in several space applications, scores 138.1 DMIPS at 100 MHz in dry zone 2, and also 180.193 core mark iterations per second. This is the second batch of MI5 benchmarks with the more complex, faster core configurations, and also with MACC pipeline or non-pipelines multipliers. Of the two variations, the pipeline MACC multiplier showed better performance at the mid and maximum frequency as the pipelining loosened timing constraint to allow higher core clocks. Both had identical performance at 50 MHz, showing that instructions per clock of both architectures were roughly the same. Also, interestingly, the MACC multipliers took up almost no more device resources or power draw compared to the fabric multipliers on the previous slide. No 5 cores performed an order of magnitude better than the MI5 cores in a minimal overhead RTMS environment. The EX1 core is most directly comparable to MI5 cores since none of them have floating point capability. The EX2 cores' extra features resulted in an additional 40 to 50% performance bump over the EX1. Considering the minor gains with the margin of error in testing, the quad-core EX4 did not show significant improvement over the single-core EX2 in these workloads. Changing the optimization setting from -02 to -03 granted a slightly better dry zone 2 scores, but worse core mark scores across all core configurations. There is no clear optimization level choice for all workloads. In these results, again, the null 5 cores vastly outperformed the MI5 cores, even with the added overhead of a Linux operating system. The EX1 core was unable to run Linux with such a limited instruction set. An EX2 core provided the best overall results, with about an order of magnitude greater performance than the best MI5 core with no operating system overhead. The overhead brings the EX2 core performance in line with the EX1 RTMS result. The quad-core EX4 showed a slight performance drop versus a single EX2 core, even with SMP multi-threading enabled in the operating system. And EX1 core was the least resource-intensive of the Null 5 cores, but not by much. EX2 provided significant gains in performance and floating point capability for a marginal increase in resource usage over EX1. EX4 required multiple times more of each resource, but showed little gain over EX2 in the workload tested. In conclusion, CoPEM Geisler Null 5 cores are recommended over microsemi MI5 cores if considering embedded CPU replacement. There was nearly an order of magnitude difference in performance in Drystone 2 and core marks between the best Null 5 configuration and the best MI5 configuration at roughly the same frequency. Additionally, the floating point support makes the Null 5 more versatile in complex workloads, showing impressive performance in the Whetstone benchmark, which the MI5 was unable to run. The Null 5 cores are also more hardware agnostic and could be tested further on other development boards, including microsemi PolarFire, Splash Kits, and Xilinx Arctic 7. After demonstrating solid compatibility with both RTMS and Linux operating systems, including networking, real-time scheduling, and file transfer, along with performance better than the UT700 CPU, which is currently used on several series spaceflight boards, the Null 5 has proven to be a capable CPU substitute for light compute workloads. Here is a list of all the references used for this project. We would be happy to answer any questions that you might have. We also would like to thank you for listening to our presentation.